Hi everyone, we're from the UCSB Bionic Vision Lab and our project was on stimulus optimization for retinal implants.
Bionic vision includes a visual prosthesis, which is an implant that provides visual perception to patients with certain forms of blindness. The way it works is by transmitting electrical signals to brain via implant. In image A, you can see the blue square, which is an electrode array in the implant. The yellow dots are the electrodes being stimulated that create percepts as seen in image B. Image B shows the percepts the user sees. We want to help the user see better by optimizing stimulus parameters with deep learning. We use a neural network to predict electrical stimuli to recreate an input image.
A previous deep learning approach was the end-to-end model. The end-to-end model took an input image and did some intermediate steps and then recreated the image to train in between. However, we only want to take part A of the end-to-end model in our project. We'll take an input image and output a stimulation protocol, which is the parameters for each electrode. The simulator used in the end-to-end model was simplified and looks like a pixelated scoreboard. We want to use a model that is more complex, but as a result, it's not invertible, so we won't be able to train using it. And this model will include the parameters amplitude, frequency, and pulse duration for each electrode. Implant placement also plays a factor, but we wanted to simplify what we had to train for.
So our methods involve 3 steps: data generation, building and training the neural networks, and then testing the models. So for our first step, we generated 2 datasets of percepts using Pulse to Percept, which is a Python package developed by the Bionic Vision Lab. We input random stimulus parameter values to generate random percept images. As you can see in the pictures, the single electrode dataset consists of just 1 percept per sample, and the multi-electrode dataset has multiple percepts per sample. We utilize 2 methods for building the networks. One is making a simple convolutional model from scratch involving these different layers as shown. And 2, using existing models such as the ResNet, which is a known and commonly used convolutional neural network, and the Vision Transformer, which is a lot newer and it uses patchwise attention. For testing, here's the overall picture of where our trained models fit in. We pass a known input image into the trained model. The model generates the corresponding stimulus parameters it's been trained to guess for, and then we input those parameters back into Pulse to Percept to generate an image again. We want this final image to be as close as possible to the original input.
So how close did we get to the final generated image to be as close as possible to the original input? We cross-reference our results by visually examining our dataset and using mean square error. We chose a couple of results from the single and multi-electrode dataset to showcase. We printed out the ground truth and the network results side by side. For the model from scratch, we obtained accurate position, brightness, and width of the spread. For ResNet architecture, we got an accurate position and streak-like appearance. But for Vision Transformer, it performed especially poorly due to the number of hyperparameters. It's possible that we were unable to find an optimal configuration for the Vision Transformer to apply to this problem. For multi-electrode, the models from scratch seem to outperform the other architectures. ResNet seems promising that it can get position and streakness accurately. This could potentially be useful for predictions of shapes or letters since they would have more of a streak-like appearance. In order to test our theory, we used the MNES dataset to see if we could get an accurate representation of the letter S. Based on our results, we would have to do further training as our network was trained on circular-like percepts.
So overall, we found that the simpler models appeared to work the best. For example, for the model from scratch, we added a dense 30 layer, which decreased the complexity, and we noticed that it improved the performance. And for the Vision Transformer, it had the greatest complexity and it performed poorly on all 3 datasets. Specifically for the model from scratch, it seemed to do well on the datasets that we generated using Pulse to Percept, which were the single and the multi-electrode datasets. But it didn't do as well on the MNIST, and we think it's because we overfit the model for the datasets we generated. The ResNet had the opposite problem of performing not as well on the single and the multi-electrode dataset, but better on the MNIST, and we think it's because we underfit that model.
In the future, we would like to create a model that is neither overfit nor underfit. Like Sriya had said, the model from scratch was overfit on the percept data, and the Vision Transformer was underfit on the MNIST data. Next, we assumed implant placement was constant, but we want to be able to predict that. Lastly, we want to recreate an image dataset like MNIST with manual percept recreations so the model can learn to recreate those images.
Here are our citations, and here are some people we would like to acknowledge. Thank you for listening.